Hey Math 1, back for part 2 of 8.11. So radioactive half-life is the last, what would you call it? Exponential application for equations that we're going to talk about. And I don't think you guys have talked about the what half-lives are in science yet. So just a very brief, unsophisticated explanation. Here goes. Let's say we're talking about a specific substance, okay? In this case, potassium 42. It's a substance that basically starts to disappear as it decays. All right? And if somebody says it's got a half-life of 12.4 hours, what that means is in 12.4 hours, this block of material has reduced to half its size. And this is how much is left over. Think of if an apple had a half-life of 12.4, think of a full apple, and then in 12.4 hours, only half the apple remains. That's kind of what's happening here. Or with potassium 42, I should say banana. At any rate, 12.4 hours later, all right, so now 12.4 plus 12.4 would be 24.8 hours total. So 12.4 more, or 24.8. Now we're half of this substance. And it just keeps cutting itself in half, and half, and half, and half, and half. Till eventually it's kind of like such a small substance, such a small amount that it's like, it's basically disappeared. But it never actually does disappear. Got it? Okay, so that's what half-lives are. And what I'm going to do is use a similar equation to what we've been talking about so far to be able to compute this pretty quickly. So what I'm going to do then is start with our new substance equaled the principal substance or the initial substance, what you had at the beginning, multiplied by 1 plus or minus r over 100 to the t power. And what I'm going to do is I'm going to try to take this equation and say, how can we alter it in such a way that it can compute the half-lives for us instantly? So here's my first question. A half-life means what's the rate of decay? Because right now we can just say the plus is gone. Yeah, it's decaying. Okay, so for the half-life equation, you can instantly just get rid of the plus. The rate of decay is always half. Half. Sorry, that didn't work out too well. So it's cutting itself by 50% every single time. The rate of decay is always 50%. So I don't have a second variable here. That r can be replaced with 50 every single time, which you can just compute. What's 1 minus 50 over 100? It's a half. It's a half. See, this is 1 minus a half, which is a half. So n is equal to p times a half. It's always going to be a half inside the parentheses to the t power. Yeah. Now the last thing we got to do is adjust the exponent, because the exponent doesn't actually reflect how much time is really going by in order to get that substance. See, think about it like this. If I were to just say, let's say that this is equal to 20 grams, okay? 12.4 hours later, we are down to 10 grams. Now, I got to take into account the fact that if I said how much of this substance remains after, 10 hours? If all I did was plug in 20 times a half to the 10th power, here's what I would get. I would get this much. The actual answer is way more than 0.0195. Look, after 10 hours, we have not even cut the substance in half. It's after 12.4 hours that the substance goes from 20 down to 10. So what we need to do is we need to say, how many times does this half-life cycle through the t-value that they give us? Okay, cycling through is pretty much just a, how do we say this? A shorthand version of multiplication and division. So what ends up being the part of the equation you need is, I need to always divide the exponent by the 12.4. I need to divide by the half-life. So the equation changes to p times a half to the t, and I'll put divided by h. The exponent is now a fraction. It's division. Which is certainly weird. You guys have not talked about fractional exponents, and you probably won't talk about them until Math 2. At any rate, let me show you how these last two examples fit into this equation. So here's the equation for radioactive half-life. So potassium has a half-life of 12.4 hours. How much of an 848 gram sample of potassium-42 will be left after 62 hours? Sorry if you couldn't see that first part. So here, we have the nu equals our principal amount, our initial amount, times a half to the t. Look, I don't know which one you prefer, fraction symbol or division. I'm just going to use the slash for division slash fraction. All right, p, what's our principal amount? It's 848. So put the 848 right here. 1/2, it's always a half. The t value, that's asking how much time is elapsing where you're computing how much is left over. That's this right here. How much of it will be left? How much of it will remain after 62 hours? The t equals 62, but then you're dividing that by the half-life, which is 12.4 hours. So then the question becomes, how do I plug that into my calculator? Well, I'm going to get back in your face here with this guy. Whoa. So it's going to be 848 times, and you know what? You can put 0.5 or 1/2 in there. It's whatever your preference is. I'm just going to put 1 divided by 2. Then I'm going to take it, caret, to the 62 divided by 12.4 power. If you do not have a calculator that gives you this, sorry, I have to rotate opposite. If you don't get that, let's see, what would you call it? That blinking exponent, actually putting it up there, you may need to put little parentheses around it. So you may need to do it like that. In fact, I would just do it like that to be careful. All right? You guys see what's going on here? Pause the video if you need to inspect it further. Here's your answer. Ooh, there's 26.5 grams left. That's your answer. So 26.5 grams of potassium-42 will remain after 62 hours. So, of course, you guys see the application for science. Like people who go into these kind of fields of science, especially chemistry, maybe biology. My playground is mathematics, so I'm not exactly sure. But I'm going to move on to the second example here. And this will be my last one for the video. So an isotope of technetium has a half-life of 6 hours. All right, H is 6. If it's given to a patient as a part of a medical procedure, What fraction of the radioisotope remains in the body after 1 day? Okay, so 1 day this is hours. T represents 1 day? Well, I think if we put this in hours, we got to put the other one in hours. There's 24 hours in 1 day. Oh, I see. Okay. And then this one doesn't actually give you a principal amount. I'm not going to give you a bunch of these in which you have to do more than just plug into the equation. So what I'm going to do is I'm going to say, oh, I get it. My bad. Okay. When they say an isotope, they're saying 1 is the value. 1 is the value. Our principal amount is 1. Darn, I got tricked by my own question. Okay, so isotope P equals 1. Half is always what's going on here, right? The T is 24 divided by the 6 hours. N is equal to 1 times, you know what? 24 divided by 6, that's 4. And I could plug this into the calculator, but I think I can do it without it. This would be 1 to the 4th, which is 1, over 2 to the 4th, which is 16, times 1. It's 1/16 of an isotope. I think that answers the question. What fraction of the radioisotope remains? 1/16. All right. So hopefully this was helpful enough for you guys to really move forward on that assignment. Hopefully this was helpful to you remote learners out there. Please email me with questions if you're completely clueless on what these notes meant and how they apply to the 8.11 assignment. All right, thanks for watching.